Okay, so in this video I want to introduce a technique called differentiation, and differentiation is the first thing that we look at as part of the broader area of maths, or maths and science, which is referred to as calculus. I would say calculus is the maths of things that are changing. And differentiation is all about finding the gradients of curves. So the gradient of a straight line is constant, but a gradient of a curve, like I've drawn y equals x squared here, varies. So down here it's got a gradient of 0, it's horizontal. In this negative quadrant it has a negative gradient, and in this quadrant it has a positive gradient, and the gradient gets steeper and steeper as you move further along. So it's changing all the time. And at GCSE, the only way we could estimate the gradient of a curve at a particular point, we did it with velocity time graphs, you may recall, is to draw a tangent and work out the gradient of that tangent, and that was our estimate. But that's not a very, very scientific way of doing it. You know, you're doing it by eye, and if 3 different people did the same tangent, you'd probably get 3 slightly different answers. So differentiation allows us to accurately say what the gradient is at any point on the curve. For any value of x, it allows us to work out the gradient. It was a branch of maths that was developed by a number of mathematicians, and in particular there were 2, Isaac Newton and Leibniz, who are, it is unclear as to who was really responsible for the first sort of development of it, and I put a link to a video which sort of goes through in a few minutes how calculus developed. It's probably worth having a quick flick through that. Anyway, here's how we know what the gradient of the line is at this point using differentiation. So this point here, let's say that this point here is x, so you know the coordinates, the x value is x, and that means the y value will have to be x squared. Okay. And what we then do is we pick another point further up the curve that's a little bit further along in the x direction. So I'm going to say that that is x plus h. So I've moved from here, I've moved along a little bit. I'm calling that little bit h. And so the y value must be x plus h squared. And what I can do is join those 2 points up, and I can work out the gradient of that red line. It's not a million miles different from the gradient of the blue line. I'm going to redraw my red line here, so I'm just going to redraw that line without the curve, just so we can see it a bit more clearly. So this point is x squared, and this point here is x plus h. Well, if I multiply this out, so that would be x plus h, x plus h, I'd end up with x squared. I'd get an xh here and an xh here, or an hx, so that's plus 2xh plus an h squared. Okay, so I'm going to work out the gradient of that straight line, and we do it by turning it into a right angle triangle, and the gradient is this distance divided by this distance, y divided by x. So the gradient is, well, if these coordinates had numbers, all we do to work out the x distance, we just say, okay, what's the difference between that and that? What's the difference between the x value here and the x value here? Hopefully you can see that that's h. That's what I did, wasn't I? I went from that point to that point, I moved along h. And if we had numbers, to work out this y distance, we just look at the 2 y values in the coordinate, and we'd ask, what's the difference between here and here? What do you get if you do that, take away that? Hopefully you can see that's 2xh plus h squared. So the gradient is this distance divided by this distance. I've got 2 things divided by 1 thing. I can therefore do some cancelling. I've got an h here, an h here and an h here, so I can divide everything by h. And what we then say is, okay, let's go back to my original diagram. I said that the red line wasn't very different to the blue line, but it's not the same gradient, is it? But if I moved this point down the curve, if I made h smaller, if I moved it down the curve, as I came down the curve, the red line would become more and more and more like the blue line. And in fact, if h was so tiny that the point was so close to the original point you couldn't see it, it would pretty much be the gradient I'm after. So what we do is we say, okay, what happens to that expression as h becomes very, very small? What's going to happen to this as h becomes so tiny that we can pretty much ignore it? And the answer is this. Now what we did here to work out the gradient is we did the difference in the y values divided by the difference in the x values. And that's why we call this formula for the gradient dy divided by dx, or it tends to be said as dy by dx. So what that means is that for the function y equals x squared, dy by dx is 2x. What that means is the gradient of this curve at any point is just 2 times the x value. So when x is 1, the gradient would be 2. When x is a half, the gradient would be a quarter. When x is minus 2, the gradient would be minus 4. I can use that formula to calculate the gradient of this function for any value of x. So what I'd like you to try, I'd like you to try that process, repeat that process for y equals x cubed. I'm going to pause the video and then show you my answer to that. Okay, so here's my very bad sketch of y equals x cubed. And here's the point that I'm trying to work out the gradient of, x cubed, and here's the point a bit further along the line, x plus h cubed. So I had to multiply this out. Now if you can remember doing the binomial just recently, you could have done it quite quickly. I did it the long way, so I did x plus h times x plus h, and took that answer and multiplied it by another x plus h, and I noticed that these two could be added together and these two could be added together. So if I redraw my diagram with my coordinates in full, this is the original point down the bottom and this is the rather horrible looking new point. Same question as before, what's that? Take away that, the x value here, take away the x value there, well that's just h as it always will be. Bit harder here, what's this? Take away this, and it's that, so that goes there. So my gradient is that, and as before, everything's got an h, so I can divide everything by h to cancel that out. So this is our formula for the gradient, and the next thing we ask is what happens as h becomes very, very small. And sorry, I'm just removing off the screen, there we go. And as h becomes very, very small, this term isn't going to be affected. But if h is so small it's almost 0, then 3x times 0 will be 0. So that will disappear and that will disappear as well. So we're left with just 3x squared. Now I realise that's something a bit new, something quite hard to get your head around, but I'm sure you'll get used to that. But the good news is that although this process, which is called differentiation by first principles, is on the syllabus, in the vast majority of situations when we want to differentiate, we don't need to, because it is predictable. So we've done two functions. You've just worked out that if the function is y equals x cubed, the formula for the gradient is 3x squared. Y equals x squared, the formula for the gradient is 2x. There is a pattern there, and there is a simple process that allows us to go from a function to its formula for the gradient. It's dy by dx, and these are referred to as differentials. And that is the next thing you will need to learn. That's the next thing we will cover.